Hello there, my dear curious physics learners. You're very welcome to your own Physics Doctor YouTube channel. I'm your own personal physics teacher, Dr. Rima McMullen. I started my teaching journey in 2002 and I have been enjoying teaching since then. Hello there, my dear curious physics learners. You're very welcome to your own Physics Doctor YouTube channel. I'm your own personal physics teacher, Dr. Rima McMullen. I started my teaching career in 2002 and I have been enjoying teaching since then. My desire and passion is to bring high quality physics education to you all. And I hope that you will all fall in love with physics and math just like I do. I'm very excited to start this journey with you all. Please share your questions and your thoughts on the content matter with me in the comment section. I look forward to interacting with you all and learning physics together. So, you might ask, what is physics? Physics is the study of the fundamental principles of the universe. Therefore, it is often termed as the fundamental science. Other kind of sciences such as chemistry, astronomy, biology, and geology, etc., they are built on the foundation of physics. Even engineering applications are based on the principles of physics. Due to its quest to decipher the fundamental construction of the universe, physics has fascinated many great minds throughout the history of time. Names such as Max Planck, Albert Einstein, Sir Isaac Newton, Stephen Hawking, and Richard Feynman need no introduction, and they were all physicists. We will begin with Physics 1, which is basically mechanics. So, this class will be useful to anyone who is taking high school physics or Physics 1 in college. Now, during this class, I'm going to assume infinite amount of potential and curiosity on your part, but I'm going to assume zero prior knowledge. Now, you might have heard that physics is heavily mathematical. I absolutely cannot deny that. Math is the language of physics. However, during this class, I'm not going to assume that you're mathematical wizards. I will teach you the math that you need to do physics. However, it will be good for you to know algebra before coming to this class. So if it's been a while since you have taken algebra, I would strongly recommend that you brush up your algebra skills. Now that you know that you're going to study about mechanics in this class, what is mechanics? Mechanics is the study of the forces acting on objects and the resulting motion of the objects. When you're talking about mechanics, you may say things such as you traveled from Dallas to New York City, traveling a distance of 1500 miles. Okay, I don't know what's the distance, I'm just making up this number. So, this is the distance. And it took you how much time? It took you 3 days. Maybe you stopped on the way. Okay. So you're going to use terms such as days, distance. Okay. What was your speed? Your average speed was maybe 70 miles per hour. Okay. So speed here. These kind of terms are called as physical quantities. Okay. Now, what's a physical quantity? It is something that can be measured. So, physical quantities can be measured. Now, what all can you measure? Can you measure temperature? Sure. You can measure temperature in degrees Celsius, degrees Fahrenheit, Kelvin, whatever you want to. What else can you measure? Can you measure the pressure, the air pressure in your tire? Yes, you can. Can you measure your speed? Yes. Can you measure force? Yes. Can you measure the duration of an event? Yes. So, all the things that you can measure, they're called as physical quantities. Now, the physical quantities are of two kinds: basic physical quantities. How about write P dot Q dot for physical quantity? And derived physical quantities. So, as the name tells, derived physical quantities are derived from the basic physical quantities. Now, what kind of basic physical quantities are there? There is distance, there's mass, and time. And these are three basic physical quantities of mechanics. And for the derived physical quantities, you can say speed, you can say force, acceleration, you can say momentum, you can say inertia, torque. Actually, every other physical quantity that you're going to see in mechanics that is not one of these three is going to be a derived physical quantity. Now, here we're talking about mechanics, right? So these three are in mechanics. However, besides these three, there are few more basic physical quantities in physics. What are they? They are, you have electric current. What else is there? Temperature. Then we have amount of matter. Then we have luminous intensity. Just want to make sure it's all fitting on my screen. So together, these seven quantities on the left side, these constitute the basic physical quantities. Out of these seven, up here, these three are in mechanics. Okay. Now, taking this a bit further, let's talk about an example. Let's say you studied for a test. Okay. For how long? 10. Whole 10. Now, did you study for 10 seconds? Was it 10 minutes? Was it 10 hours or 10 days or maybe it was 10 years? Or who knows, maybe it was 10 decades. So you can see that 10 by itself doesn't give much information, does it? Like you just saw, it could be 10 seconds, it could be 10 days, it could be 10 years, it could be anything. So all these words that I'm writing after the number 10, these are called as unit of measurement. This is the reference with respect to which the measurement is made. This tells you whatever you're measuring, how much of that is there, right? If, for example, if we're talking about time, okay, so if you say that it is 10 seconds, it's telling you that it's a small amount of time. Versus if you said it was 10 days, that's way more time than 10 seconds. And similarly, if you're talking about distance, if you said just 15, doesn't give you much information. 15 miles, it gives you information. But had it been 15 feet, then if I hadn't told you whether it was feet or miles, would you be able to tell me the difference between one 15 and the other 15? Absolutely not. I have to tell you that the distance that I'm talking about, if it's 15 miles, 15 feet, 15 inches, or 15 kilometers, only then you will get an idea of the extent of the distance traveled, right? So these units of measurement are extremely important. And for our basic physical quantities, which were, we said it was a distance, okay, it's the C. Does it look like C? Sure it does. Mass and time. In physics, we have defined different systems of units, okay? And one of the systems is called as CGS, okay? What do you think the C stands for? Centimeter. Lowercase c, lowercase m. It is centimeter, okay? Grams, that is G. Lowercase g. Now, in physics and chemistry, many things are case sensitive. If you use uppercase G, it's not grams. Especially, I mean, if you're using prefix, for example, this is millimeter, this is megameter. Huge difference. M, M, totally different meanings. This is 10 to the power negative 3 meters. This is 10 to the power 6 meters. So case does matter. Pay attention to the case. Okay. All right. Back to the units of the time. S. What do you think S stands for? Seconds. So CGS, centimeters, grams, seconds. Then we have FPS, foot, pound, second. See? Foot, pound, second. Another system of units, MKS. So what do you think M stands for? Did you figure it out? Did you guess it? Let's see if you guessed it right. Meters. Okay, you guessed it right. K. What do you think K stands for? It's kilograms. S. Seconds. So this MKS system, this has a special name. It is called as SI system. SI system is System International. Okay. Now System International is the system of units that's widely used in science across the globe. Now what's the benefit of using SI system in which the units are meters for distance, kilograms for mass, and seconds for time? The benefit of the system is that SI system is metric system of units. What does metric mean? Do you know? Any guesses? Metric system means it is based on powers of tens. How? All right, we were talking about kilograms. 1 kilogram, you want to convert it to grams. 10 to the power 3, powers of 10. 1 centimeter, convert it to meters. 10 to the power negative 3 meters. Okay, and 1 mega second, 10 to the power 6 seconds. Let's talk about some of the metric prefixes. So we know that 10 to the power 0 is just 1. If I go to 10 to the power 1, that is called deca. So if I have like a deca meter, it will be 10 meters. Okay. 10 to the power 2 is called as hecto. 10 to the power 3 is kilo. Then we go to 10 to the power 6. Once you get to 10 to the power 3, then after that you're going to go up by an order of magnitude of 3, which means you get to 10 to the power 6, which is mega. Then we have 10 to the power 9, which is giga, okay, like gigabytes. So if I say something is gigameters, that is 10 to the power 9 meters. If I say 1 hectoseconds, sorry, this is seconds here, that will mean 10 to the power 2 seconds. Okay. So these metric prefixes are used for large number. What kind of metric prefixes would you use when dealing with small numbers? For small numbers, the metric prefixes are like 10 to the power negative 1. This is deci. 10 to the power negative 2, centi. 10 to the power negative 3, milli. 10 to the power negative 6, micro. So you might notice that after 10 to the power negative 3, I move to 10 to the power negative 6. 10 to the power negative 6 is 3 orders of magnitude smaller than 10 to the power negative 3. Now, if you will go to these large numbers, you will see here as well, after 10 to the power 3, I went to 10 to the power 6. So I'm doing the same thing here. After 10 to the power negative 3, I'm moving on to 10 to the power negative 6. So there's a pattern there. Now on, I will go with orders of magnitudes of 3 here. Next is 10 to the power negative 9, nano. Next will be 10 to the power negative 12, which is pico. 10 to the power negative 15, femto. Then comes atto for 10 to the negative 18, and so on. So what do we mean? If I say 2 microseconds, so here this is represented by micro. This is the symbol for micro. This is 2 to the power negative 6 seconds. Now, talking about the symbols, symbol for deci is lowercase d. Symbol for centi is lowercase c. Symbol for milli is lowercase m. Symbol for micro is here. It's a Greek letter. Nano, lowercase n. Pico, lowercase p. Femto, lowercase f. So other than micro, they're all regular English letters. And similarly, for these large numbers, what are the symbols for the prefixes? Uppercase D for deca, uppercase H for hecto, uppercase K for kilo. I've seen even lowercase k being used actually. Uppercase M for mega and uppercase G for giga. Okay. So if I say something is 2.79 nanometers, what is it in SI units? You will say that's 2.79 times 10 to the negative 9 meters. Now this right side, this is now in scientific notation. Here. Okay. All right. So this was about the metric prefixes. Next thing that we're going to discuss is the dimensional analysis. Now, dimensional analysis doesn't get as much importance as it deserves. It is a very important tool to figure out if your equation is correct or not. You can actually sometimes even figure out the equations, the formula using dimensional analysis. Now, what is dimensional analysis? In dimensional analysis, we are saying that mass has unit m to the power 1. Okay. Length or distance has the dimensions of L. My bad, I said units of M, I meant dimensions M. And time has dimension, just T to the power 1. So when you're talking about some physical quantity such as speed, which is defined as distance divided by time. Okay. Now, what are the dimensions of speed? So these square brackets, these represent dimensions. Distance is L to the power 1. Time is T to the power 1. However, for dimensional analysis, we also have to include M. So I'll say it's M to the power 0 because there is no mass in the equation for speed. So I can write this as M0 L1 T to the power negative 1. If you're given these dimensions and you're asked what kind of physical quantity is that, then you know that this physical quantity does not have mass in it. Why? Because mass has power of 0. It has 1 unit of length and T to the power minus 1. So it has second inverse if you're talking in the SI units. So this is dimensions of speed. Okay, another one, let's talk about force. Force is mass times acceleration. All right, mass. Now, acceleration is change of velocity over change of time. So, let's write it like this. Rate change of velocity with time. Now, what is rate change of velocity with time? You can write this as del over del t of delta distance. Let's just write delta d for distance over delta t. So this may not be making much sense to you yet, but if by any chance you're familiar with calculus, then that's this thing here. This is your force. Okay. So what I'm saying is that force has units of mass, 2 units of time inverse, and 1 of distance. So if I were to write the dimensions of force, I would write, let's see, let me change the color, 1 of mass, m1. Here, 1 of distance, L1. There are 2 t's at the bottom. That's t to the power minus 2. Because 2 t's in the bottom means 2 negative t's in the numerator. So this is the dimensions of the force. Okay. What else? Pressure is force per unit area. Now I already know force. It's m1 L1 t minus 2. And what is area? L squared, right? Because area is length times length. So it's L squared. Now what you can do is bring this L squared from the bottom upstairs here. That will subtract from this one, right? This 2 subtracts from this one up here. T to the negative 2. M, L minus 1, T minus 2. These are dimensions of pressure. Okay. Let's see. So let's say you're given this expression where A is acceleration, K is a dimensionless constant. Means that K could be 2, 3, 4, 5, whatever. We have to figure out the correct number for N and M. What is N and M going to be? Okay. So I know that acceleration is length t to the power minus 2, m will be 0, L is 1, right? These are your units of, these are the dimensions of acceleration on the left side. On the right side, K doesn't have any dimensions. R, what are the dimensions of R? That's just distance, L. And this is going to have power, N. Then we have V. V is L1 t to the power minus 1. But they are both raised to the power of m. So there's an m here, there's an m here. It becomes like this. All right, so I have m to the power 0, L to the power 1, t to the power minus 2 on the left side. On the right side, I have dimensionless constant k. There's no m here either, so I can write m to the power 0 if there's no m on the right side. Then I have this L to the power n and L to the power m. Whenever the bases are same, which is L, you can add the exponent. So it becomes m to the power m plus n, right? Or I should maybe say n plus m just to be consistent here. N plus m. And lastly, we have this t to the power minus m. Now what you're going to do is you're going to compare equal dimensions, right, on each side. L to the power 1 gets compared with this L to the power n plus m, right? Then we have this t to the power minus 2 on the left side. On the right side, I have t to the power negative m. So what does this give me? This gives me that minus 2 equals minus m. Because t, the base is same. If the base is same, that means their powers also equal each other. So this gives me m equals 2. Now, from this first equation, L to the power 1 equals L to the power n plus m. This gives me the bases equal. Therefore, the powers must also equal each other, n plus m. Now, here, if in this case, if m is equal to 2, then n will be equal to minus 1, right? With that, what do we get over here? This gives us A equals K V to the power M, which is 2, R to the power minus 1, so R comes at the bottom here. So this is your equation. This is actually kind of centripetal acceleration that you will learn when you get to the circular motion. I hope this made sense. Newton's law of gravity can be written as F equals G m1 m2 over r squared, where F is force, m's are the m1 and m2, these are the two masses of the two objects, and r is the distance between the center of those two masses. Okay, now figure out from dimensional analysis the units of G. What are the units of G? Use dimensional analysis to figure out the units of this constant G. This is called as universal gravitational constant. Okay, let's do this. Now, force is going to be, I'll give it to you, mass times acceleration. These are the units of, these are the dimensions of force. I'm so used to saying units that just keeps coming out of my mouth instead of dimensions. So please pardon me on that. I want to find out the dimensions of this G. Once I know the dimensions, I can figure out its units. Mass 1, m. Mass 2, m. R squared, L squared. So the right side, I can rewrite this as m squared, L to the negative 2, t is 0 there, right? And on the left side, I have m1, L1, t to the power negative 2. Okay. So what you can do is divide both sides by m to the power 2, L to the power negative 2, t to the power 0. So obviously it cancels out on the right side. And now I'm going to swap left and right sides. So G comes on the left side. And the right side now becomes m1 L1 t to the negative 2 square brackets, bottom square brackets, m to the 2, L to the negative 2, t to the 0. Okay, good. Now what I'm going to do is, you can make your life easy and say that everything that's in the denominator, you can bring it upstairs and change the sign of its power. Or you can do the technically right thing. You can say, okay, I'm going to multiply, divide by m to the negative 2, L to the plus 2, t to the 0, because that doesn't really matter. M to the negative 2, t to the plus 2, sorry, this is L, not t, my bad. L to the plus 2, t to the 0. So what will happen at the denominator? These two combine and their powers will add up. Why? Because the bases are same. So 2 and minus 2 add up to give you 0. So it becomes m to the 0 at the bottom. Similarly, L to the minus 2 and L to the plus 2, it becomes L to the power 0 and t to the power 0. What do we get upstairs? Upstairs we'll get m, this one, and this minus 2. Okay. L, this one, and this plus 2 here. 1 plus 2. T minus 2 and 0 is minus 2. So this becomes m to the power, let's not forget these square brackets, m to the power minus 1, L to the power 3, t to the power minus 2. So the units will be L squared, it's at the top because it's positive power, meter cubed over, here mass, kilograms, second squared. Okay. Now, is this right? Honestly, I don't know. Just by looking at it, I totally can't tell, but I can figure it out. How? I know that F equals G m1 m2 over R squared. In this equation, I'm going to multiply by R squared divided by m1 m2. Same on the left side. So what does this give me? Cancelled, 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 cancelled. Swap left, right. G is F R squared m1 m2. Okay, good. Now the force is kilograms meters per second squared because it's mass times acceleration times. Now I'm going to write these ones here. I meant to change the color. Units of these. So meter squared comes for this R squared divided by kilogram for this M1 and another kilogram for M2 becomes kilogram squared. So one of these kilograms cancels this kilogram at the top and I'm left with meter times meter squared. Gives me meter cubed, this kilogram times second squared. Look here. Same thing. So we did the dimensional analysis for G absolutely correctly. Now this G, which is the universal gravitational constant, is going to be very similar to something else. Look here. This is Newton's law of gravity. Look at this other equation here. This says F equals K Q1 Q2 over R squared. This is Coulomb's law. Can you figure out the dimensions and the units of Coulomb's constant K? NSION, dimensions and units of Coulomb's constant K. Lowercase k, by the way, okay? So I'm going to leave this as an assignment for you. I will do this in the next lecture if you can do it on your own. Check your answer, okay? So in this lecture, what did we do today? We started out with what is mechanics, okay? We said that mechanics is the study of forces that act on an object and how those forces alter the motion of that object, okay? Then we talked about, okay, get back here, the physical quantities. Anything that can be measured is a physical quantity. We said physical quantities are of two kinds, basic and derived. There are three kinds of basic physical quantities in mechanics, which are mass, distance, and time. However, in physics, there are some more basic quantities: electric current, temperature, amount of substance, and luminous intensity. Now, very quickly, let's talk about the SI units of these. Amperes for current. Okay. Temperature, Kelvin. Amount of substance, mole. Luminous intensity, candela. These are the SI units of these other four physical quantities, which are basic physical quantities, but they're not in mechanics. Every other physical quantity that's not one of these seven, what is that called? That is called as a derived physical quantity. Then we talked about the units of measurement, and we said that for these basic quantities, the units of measurements are CGS, centimeter, gram, seconds. FPS, which is very common in the United States, foot, pound, and seconds. And the last we said was MKS, meters, kilograms, seconds, which is also the SI system of units, System International, which we use predominantly in science. Now, why do we use SI system? What's so great about it? Well, it's metric system. It's based on powers of tens. Makes things very easy. Then we looked at some metric prefixes. Okay. After that, we moved on to the dimensional analysis. So next time, we're going to look at significant figures. After doing that, we're going to move on to the motion in one dimension. So that was today's class. Please let me know in the comments, how did you like the class? What did you like about it? And what you did not like about it? And when you tried about what you did not like about it, just be a little kind to me, okay? It takes me a long time to make these things. If I can improve in any way, I would love to. Let me know your ideas. I will definitely try my best to incorporate those. With this, I'll end this lecture. I hope that it was useful to you, and I'll see you again very soon in our lecture number 2. Have a good one.